Going to show several examples of integration using U substitutions, and this is an extremely valuable and useful tool in integrating any sort of composite function, and most functions they tend to be composite functions. Now the idea we start with is if we want to integrate 2 cosine x, that is not a problem. However, if we want to integrate cosine of 2x, because of the 2 in there inside, it's sort of think in terms of a reverse chain rule, and so you have to think, well, what would I differentiate in order to get this? But there's a more systematic way to go about it using what we call the U substitution, and I'll show many examples of that. Another thing I want to point out before I get into those examples is a few vocabulary words which go along with what we're doing around this set of math skills, and that is that displacement of a body is the integral of velocity, and displacement is the final position minus the initial. So if you go somewhere and then come back, your displacement is 0. So displacement is your integral velocity, whereas your total distance traveled, which would mean if you go somewhere and come back, you actually have traveled some distance, is your integral of speed. And your speed is your absolute value of velocity. And so speed is a scalar, velocity is the vector. So that's how we relate displacement, velocity, speed, total distance traveled. So now on to some examples of U substitution. We have the integral x squared plus 1 squared times 2x dx. Now, a thing to note is that if we choose x squared plus 1 to be what we call u, then the derivative du dx is equal to 2x. But what we tend to do is just move the dx over. So now we have du is 2x dx. So this x squared plus 1 squared is u squared. This 2x dx is du. So now I'm integrating u squared du, which is simple power rule. So I've got 1/3 u cubed plus c, and then I plug back in x squared plus 1. So 1/3 x squared plus 1 quantity cubed plus c, because it's an indefinite integral. So what you want to try to do is find the u such that your du is some form of what's left. And when I say some form, I'm implying that you can multiply by constant multiples, and we'll do that in a little while. So in this case, if you make u equal to 5x, then your du would be 5 dx, because it's du dx is 5, you multiply the dx over. So here I've got my u, the 5 dx is my du, so I just put the 5 and group it with my dx. So now you see I've got integral of cosine u du, integral of cosine is sine u plus c, and you plug back in your 5x. So there you go. Okay, in this example, if you make u equal to x squared plus 1, your du is 2x dx. But note that I only have a single x. I want that to be a 2x, so what I do is I multiply 2 on the inside, and to compensate, I put a half on the outside. So now I have a half times the integral of 2x, x squared plus 1 squared dx, because these two pieces here are going to be my du. So I have a half. Here's my u squared, and these two pieces make my du. So I integrate u squared. I've got a half times a 3rd u cubed plus c. This is 1/6, and I plug back in my x squared plus 1 for u. So this is multiplying inside and outside by a scalar in order to get my du to match up correctly. Same idea over here, x times x squared plus 1 to the 8th. I'll make u x squared plus 1 because then my du will be some form of what's left. I've got an x dx here. This is 2x dx, so when I say some form, I have to put a 2 on the inside, which means I'm going to have to put a half on the outside to compensate for that too. So now this 2x dx is a du. X squared plus 1 to the 8th is u to the 8th power. So now I've got this integral, simple power rule, 1/9 u to the 9th plus c. Multiply those, plug it back in, x squared plus 1 for u. Okay, in this case, if I make u equal to 2x minus 1, and well, first thing is just to forget about the radicals, use rational exponents. If I make u equal to 2x minus 1, my du is 2 dx. And I have a 1 dx. You don't see anything there, so think of it as 1 dx. So I need a 2 on the inside, right here, which would imply I need a half on the outside to compensate for it. Write it in terms of u, 1/2 integral of u to the half du. So here's my half. This becomes u to the 3/2 divided by 3/2, but divided by 3/2 is the same as multiplying by 2/3. So 2/3 u to the 3/2 plus c. Multiply these, you get 1/3 2x minus 1 to the 3/2 plus c. Okay, this is where it starts to get a little more complicated. This type I call back substitution. You've got to sort of substitute back in. The idea is to get everything, remember, in terms of u's. But in previous examples, If we pick u equal to 2x minus 1, which we're going to do again here because it's inside a radical, then we'd have a form of what was left. But this time we don't, because our du is 2dx, but I have this x floating around here that you can't multiply x's inside and outside, only with constant multiples. So I've got to figure that out. So what I do is I take my substitution equation and I solve it for x. So now that I've got x in terms of u, I can put the u plus 1 over 2 in for this x. So I've got this divided by 2 I put out here as a half. Actually what I did here was I simply just got my du to match up. I needed 2 dx, so I put a 2 on the inside, half on the outside. Okay, so that was my step there. The next step is to get the u's in place. So here's my half. My x is the same as u plus 1 over 2. 2x minus 1 to the half is u to the half, and 2 dx is du. Now I can distribute the u to the half. So you can't distribute up in here into the radical, but you can distribute this radical in with these others. And so I took the 2 out front, made it a 1/4. U to the half times u to the 3 halves, u to the half times 1 is u to the half. So that's the key thing, is here you're not allowed to distribute, but down here you can. And I integrate each of these, plus c, and I put a c1 because I'm going to multiply it by a quarter, so it's, strictly speaking, it's a different random constant. And finally I plug back in 2x minus 1 for u. So there's my answer. So the key step is this back substitution, and what we realize is that our du is different from what we have left over. So another example of this, make u what's inside the radical. So u is x minus 1, and du is dx. So now x is u plus 1. So I can rewrite the integral as this is u plus 1. This becomes u to the half. I distribute. I would integrate using the power rule. When I'm done, plug back in x minus 1 for u. If you start with x's, you got to finish with x's. Longer example here, but same idea. U is x minus 2, so x is u plus 2, du is dx. Write everything in terms of u's, multiply this out, distribute, integrate term by term, and then plug back in x minus 2 for u. Okay, for this example, rather than making u something like 3x, remember the idea is hopefully to make u something such that your du is a form of what's left. So if I make u not just 3x, but sine 3x, my du is 3 cosine 3x dx. This 3 is from the chain rule. So because I've got a 3 there, I'll need to have a 1/3 out front to compensate. So I just put a 3 in with this. So this is now u squared. This is du. So here's my integral, 1/3 integral of u squared du. Simple power rule, plus c of course, and plug back in sine 3x for u. Over here, same idea. Make u cosine x, so du is negative sine x dx. Well, I have a sine x dx, but I need to put a negative on the inside. So I put a negative on the inside, which means I need to have a negative on the outside to compensate. And so it becomes this integral. Integrate with the power rule, plug back in cosine when you're done. Okay, now we have definite integrals. So same idea, but a little different because there's limits. U is going to be x cubed minus 1, because then if I have du is 3x squared dx. Notice that I've got a 2x squared dx. So if I simply multiply by a 3 halves on the inside, I would make the 2 into a 3. But if I'm going to do 3 halves on the inside, I have to put a 2/3 out front. Now, when I change everything to u, it looks like this. This 3x squared dx is a du, x cubed minus 1 is u. Here's the 2/3, but notice my limits are different, and that's because these are x values. So if you plug in 0 into your substitution equation, 0 cubed minus 1 is negative 1. If you plug in 1, 1 cubed minus 1 is 0. So the limits change. If you put 0 and 1 here, strictly speaking, it's incorrect because your integral should be in terms of u values. So then I can go on and integrate it. So I've got 2/3 half u squared, going from negative 1 to 0. But because everything's in terms of u's, you don't have to go back to x's now. You can just evaluate it as it is. And so 1/3 u plus 1 equals a 1/3. Now over here, the point I make is that I leave it blank. I don't put the limits in, so I integrate it, then I go back to x's, but because I went back to x's, I used my original limits of integration. But you're better off just changing your limits and then keeping everything in terms of u. Okay, this problem here, again, we have a definite integral. I make u 2x squared plus 1, so my du is 4x dx. I've got a 3x dx, so if I multiply inside by 4/3, I need to multiply outside by 3/4. So the 3x dx became a 4x dx, which is my du. This is all u to the half. Again, my limits change. If I plug in a 0, 2 times 0 squared plus 1 is 1. 2 times 2 squared plus 1 is 9. So here's my 3/4. I integrate, and I get 2/3 u to the 3/2 going from 1 to 9, and you plug it in. Now, the last thing I show down here is the idea that the red one is in terms of u. So that's if I were to actually go ahead and actually the blue is, I think the blue is the u to the 1/2 going from 1 to 9, and the red is this function x going from 0 to 2, and the idea is that these areas are supposed to be the same, and they do look to be about the same. A couple more examples. Tan x secant squared. A couple ways to do this. Make u tan x, and then your du is secant squared, so you simply have u du, which is half u squared plus c. So that's half tan squared x plus c. However, I could also split off a secant and write it like this. And now in doing this, I make u equal to secant x. Du is secant x tan x. So again, I have u du half u squared plus c. And that becomes half secant squared x plus c. So same integral, and yet I get different answers, or so it seems. The idea is that these differ by a constant. This actually turns out to make sense because these are connected through this Pythagorean identity, so they differ by the 1 in the identity, and so that can be accounted for in your random constant. We can do the same sort of thing with sine and cosine. If I make u equal to sine, du is cosine x dx, so I end up down here, half sine squared x. However, if I make u cosine, du is negative sine x dx, so I have to put a negative on the inside, negative on the outside, and I end up getting negative half u squared plus c. So again, they differ by the negative and also by the constant, but that can be accounted for by this Pythagorean identity. One other way to do this, we're really looking for other ways, is to start off with a double angle formula. I put a 2 on the inside and put a half on the outside. Now the reason I put the 2 on the inside is because 2 sine x cosine x is the same as sine 2x. So now if I let u equal to 2x, my du is 2 dx, so I need another 2 on the inside, which means I need a half on the outside, so it makes this a 1/4. Write it in terms of u's, integrate it, negative 1/4 cosine u plus c, plug back in 2x for u. So apparently this is also an answer, which can be shown to be equal to the previous two through a double angle formula for cosine.